Imagine looking up at the night sky in 2029 and realizing that something the size of a skyscraper is rushing past our planet, closer than the very satellites that power your phone and guide planes across the globe. Not science fiction, not a movie plot, a real event. Yet, while most of the world is busy being dazzled by a harmless traveler from another star system, almost no one is paying attention to the giant object that will streak by Earth in the closest recorded pass of its kind. We should be asking ourselves why the headlines celebrate the wrong visitor. The truth is, the real story is not the mysterious interstellar comet making a polite flyby. It's the massive neighbor barreling straight into our backyard. And what makes this even more astonishing is that almost nobody is talking about it. The buzz right now is all about an icy wanderer known as 3I Atlas. Scientists describe it as only the third confirmed interstellar object ever to pass through our solar system. It's drifting in from the depths of space, trailing a faint veil of dust and vapor as sunlight ignites the frozen surface. To the public, it feels exotic, almost alien. Magazines call it an extraterrestrial visitor. News outlets latch onto it because the story practically writes itself. After all, a comet from another star system sounds far more thrilling than another asteroid whizzing past Earth. The timing, too, adds to the drama. Around October 30th of 2025, this icy body will reach its closest point to the sun before swinging back out into the void. The spectacle will be beautiful, no doubt, but beauty doesn't equal danger. For perspective, 3I Atlas will be nearly 270 million kilometers away when it makes its nearest approach to Earth. That's so far that you could fit the distance to our moon almost 700 times into the gap between us and the comet. In cosmic terms, it's waving from another neighborhood entirely, and that's the irony, it's completely harmless. At no point will it intersect our orbit. The math is straightforward, the orbital calculations precise, the verdict final, zero threat. NASA's Planetary Defense Office has been vocal about this, and the European Space Agency repeats the same message. No tricks, no cover-ups, just physics. Yet despite the certainty of safety, the fascination continues. The reason for the hype is simple. Interstellar visitors are rare. Astronomers have only confirmed 2 before Atlas. The cigar-shaped Oumuamua discovered in 2017, and Comet Borisov spotted in 2019. Both shocked the scientific world, revealing fragments of distant star systems drifting freely through the galaxy until chance brought them into our line of sight. These objects act like frozen messages in a bottle, carrying chemical signatures from environments our telescopes cannot reach. 3 Atlas is another opportunity for science to peek at material forged far away and long ago, perhaps millions of years before Earth itself even existed. That kind of discovery lights up imaginations, which makes for great headlines. As it glides closer to the sun, telescopes like Hubble capture incredible images of its glowing coma, the halo of dust and gas boiling off its icy core. The visuals are undeniably stunning. Early November skies will likely give amateur stargazers their own glimpse, sparking a frenzy of telescope photos across social media. In that sense, Atlas is delivering exactly what we expect: a picturesque show, a scientific curiosity, and a reminder that our solar system is not as isolated as we sometimes think. But here's the catch. While we're busy marveling at this cosmic tourist, we're overlooking a very different kind of traveler, one that doesn't hail from faraway star systems, one that actually shares our cosmic neighborhood and plays by entirely different rules. Lurking in the background of astronomical research are the so-called near-Earth asteroids. These are chunks of rock and metal, forged in the same ancient disk of dust that built Earth itself. They are not glamorous. They don't sparkle with alien mystery. They don't get front-page coverage. Yet these are the ones that really matter. Because unlike interstellar comets that swoop by once and disappear forever, near-Earth asteroids repeatedly cross paths with our orbit. Some miss by comfortable margins. Others pass within lunar distance, closer than the moon, closer than many of the satellites we rely on. And they do this regularly, not once in a century, but dozens of times every year. Think about that contrast. The supposedly alien comet 3I Atlas will be nearly 268 million kilometers away at closest approach. Meanwhile, small near-Earth objects slip past us within a mere 400,000 kilometers all the time. sometimes without anyone outside the scientific community even hearing about it. Yet it's the faraway comet that gets the headlines, while the closer, riskier objects are quietly logged in technical bulletins that most people never see. The media loves a mysterious visitor. What it struggles to sell is the danger already sitting on our cosmic doorstep. And this is where the real story begins. Because in 2029, not long after the interstellar visitor fades from memory, a colossal asteroid will slide between Earth and the Moon in the closest pass of its kind ever recorded. It's called Apophis, a mountain-sized body of rock and metal racing through space at over 7 kilometers per second. Unlike Atlas, Apophis doesn't come from some exotic corner of the galaxy. It was born right here in the same solar nursery as our planet, and it has spent billions of years orbiting the Sun just as we do. What sets it apart is its trajectory, an orbital path that happens to bring it terrifyingly close to Earth. This isn't speculation. This isn't vague. What if? The orbit has been calculated and confirmed by multiple space agencies. On April 13th, 2029, Apophis will pass only 31,000 kilometers above Earth's surface. To put that into perspective, our weather and communication satellites sit at about 36,000 kilometers. That means this massive object will pass closer than the machines we use every day to talk, navigate, and forecast the weather. For the first time in human history, an asteroid of this scale will come close enough to watch with the naked eye from the ground. No telescope, no binoculars, just step outside, look up, and there it will be, blazing across the sky. Yet for reasons that almost defy belief, Apophis has not commanded the same public fascination as the comet. No viral headlines, no social media countdowns, no breathless articles describing its passage as alien. The public conversation has been consumed by the beautiful but harmless Atlas, while the enormous, undeniably significant approach of Apophis barely registers. This is the great cosmic misdirection. While the world stares at a glowing tourist, the actual neighbor knocking on our door is quietly approaching. Scientists stress that Apophis is not expected to impact Earth in 2029, but its approach is still monumental for planetary defense research, space policy, and public awareness. Because unlike comets from beyond the stars, asteroids like Apophis are the ones we truly need to understand. They're the ones with the potential to change the course of human history, not by sparking wonder, but by striking with devastating force, if ever the trajectory lines up wrong, and ignoring that reality, because it lacks the alien hook, might be the most dangerous oversight of all. So as we watch Atlas glow and fade, the real question is not about interstellar visitors at all. The real question is why humanity is not preparing for what's about to sweep right past our planet. Because in 2029, the sky will host a moment unlike anything we've seen in modern history. And this time, it's not a distant traveler, it's a neighbor. The truth about space hazards is that the most devastating impacts in Earth's past never came from distant, exotic wanderers. They were homegrown threats. The asteroid that ended the reign of the dinosaurs, slamming into the Yucatan Peninsula 66 million years ago, was part of our own solar system. The Tunguska blast in 1908, which flattened thousands of square kilometers of Siberian forest, was caused by a small object that broke apart in the atmosphere. Even the Chelyabinsk meteor of 2013, just 20 meters wide, exploded with the power of a nuclear weapon and injured over 1,000 people in modern Russia. None of these came from other stars. They were ordinary space rocks, following ordinary orbits, crossing paths with Earth at the worst possible time. And that's the point. The danger we should worry about isn't an icy stranger from Alpha Centauri screaming past at impossible speeds. The objects that keep planetary defense experts awake at night are far less exotic. They're the chunks of rock and metal already circling our sun, moving along stable orbits that occasionally intersect with ours. They don't glow like comets. They don't come with flashy tails. They don't inspire headlines about alien origins, but they are the ones that can truly ruin our day. So while 3i Atlas dazzles observers with a brilliant light show as it accelerates to more than 40 kilometers per second near perihelion, we need to keep perspective. That spectacle is harmless. The real risks are far quieter, hidden among the countless bodies orbiting in our neighborhood. They don't announce themselves with firework displays in the sky. They just move silently, following paths set millions of years ago, waiting for the wrong gravitational nudge at the wrong time. Before we dive into the asteroid that once rattled scientists so much that it triggered emergency meetings, let's pause and consider what Atlas can actually teach us, and what it can't. Because here's where the hype around interstellar visitors often collides with the practical realities of planetary defense. What makes Atlas valuable is not its size or its speed. Early measurements suggest its solid core may be only a few kilometers across, perhaps even smaller once you strip away the bright haze of gas and dust surrounding it. In fact, many asteroids that routinely pass close to Earth are larger. What makes this object scientifically important is its chemistry. It has been wandering between stars for millions, maybe billions of years, soaking in cosmic radiation, surviving the freezing emptiness of deep space, and carrying with it whatever materials it formed from in some distant stellar nursery. It's a messenger from another world, a frozen time capsule from far beyond our reach. That's why telescopes across the globe are locked onto it. The James Webb Space Telescope is breaking down the starlight that reflects off the comet, splitting it into spectra that act like fingerprints for different molecules. Hubble continues to capture images of its dusty shroud. Radio observatories are listening for faint signals from gases escaping its surface. Even small observatories are pitching in, measuring how sunlight bounces off its particles to learn about their texture and composition. The entire network of planetary science is mobilized, determined to extract every last clue before the comet vanishes forever. But here's the reality check. None of this helps us prepare for a collision. Atlas cannot teach us how to deflect an asteroid. It cannot help us model impact scenarios. Its trajectory ensures it will never come near Earth. And that's not just luck, it's physics. Interstellar objects are poor candidates for impact hazards because they move too fast on open-ended hyperbolic paths that cross the solar system once and then vanish. They don't linger, they don't return, they don't threaten. Contrast that with the objects that actually matter. Near-Earth asteroids move in looping elliptical orbits, cycling around the sun on paths that sometimes intersect ours. They come back again and again, sometimes every few years, sometimes every few centuries. And those orbits aren't fixed forever. Gravitational nudges from planets can shift their paths. The constant push and pull of sunlight, known as the Yarkovsky effect, can gradually alter their trajectories as absorbed heat re-emits into space. These subtle changes can mean the difference between a safe pass and a direct hit centuries later. That's why near-Earth asteroids demand attention. They carry proximity, probability, and persistence, the three factors that define real danger. This is where the conversation about risk often gets distorted in the media. Danger in space isn't measured by mystery or beauty. It follows a simple calculation: how close an object comes, how massive it is, and how likely it is to cross our path again. Atlas fails that test completely. It's far away, fast-moving, and gone forever after this single visit. In other words, all spectacle, no threat. Yet every time an interstellar object like this is spotted, the coverage follows the same script. First, an excited announcement about a visitor from another star, then somewhere buried in the story, a quiet assurance that there's no danger. After that, weeks of speculation about strange shapes, alien origins, or exotic chemistry. The one thing usually missing, any meaningful discussion about the asteroids that actually pass within the orbit of our moon every few weeks. Those are the ones that could cause real problems. Those are the ones that don't get flashy headlines. Take a look at NASA's database, and you'll see a constant stream of near-Earth objects with designations like 2024 PT5 or 2025 RX12. Each one is carefully logged, their orbits calculated, their future approaches predicted. Most are small, most pass harmlessly. But they are real, they are close, and unlike Atlas, they matter. These are the asteroids that demand the technology of planetary defense, the kind of technology we are only just beginning to test. That's why missions like NASA's DART project made history. In 2022, a spacecraft deliberately slammed into a small moon called Dimorphos that orbits the larger asteroid Didymos. The impact was a test to see if we could nudge an asteroid's orbit. The result shocked even the mission planners. The orbital period of Dimorphos shifted by over 30 minutes, 3 times the minimum change needed to declare success. For the first time, humanity proved that we could alter the path of a celestial body. That's planetary defense in action. And DART was just the start. The European Space Agency launched the Hera mission in 2024 to follow up on that experiment. By late 2026, Hera will arrive at the Didymos system to analyze the crater left behind and measure the impact in unprecedented detail. Together, these missions form the foundation of a new field, one that focuses not on interstellar visitors, but on the near-Earth asteroids we might one day need to deflect. Atlas, for all its beauty, contributes nothing to this effort. Its hyperbolic escape path means it's slipping through the solar system, like a tourist, unaffected by the subtle forces that shape the orbits of local asteroids. It cannot be used as a practice target. It cannot help refine deflection strategies. It cannot prepare us for the moment when a real threat appears. So yes, Atlas is fascinating. It's worth the observations, the science, the excitement, but when it comes to survival, it's irrelevant. The real work lies in tracking, modeling, and preparing for the objects that don't make headlines, but could one day alter the fate of our world. You can't change the path of something already racing out of the solar system at escape speed. And that single fact highlights an often missed truth about risk and how we talk about it. What captures headlines or sparks wild imagination isn't always what's actually dangerous. A visitor like 3i Atlas fascinates us precisely because it feels so alien, so far from the familiar, an interstellar traveler carrying secrets about the birth of planets and systems light years away. But the same qualities that make it exciting are what strip away the real danger. Wonder and risk operate on completely separate tracks. What truly threatens us are not the rare outsiders, but the countless ordinary neighbors quietly circling our sun. Those neighbors come in familiar varieties: the S-type asteroids, built from silicate rock mixed with nickel and iron; the C-types, dark bodies rich in carbon compounds and reservoirs of water; the Q-types, likely fragments of once larger asteroids shattered in long-forgotten impacts. These are the ones worth losing sleep over. They move within our cosmic neighborhood, crossing paths with Earth often enough that chance alignments eventually matter. From now until early September, Comet 3i Atlas will be visible in the evening sky. Then for a few weeks, it'll sink too close to the sun's glare to be seen. By November and December, it will return brighter than ever, freshly energized from its solar encounter, and again clear of the blinding sunlight. This short viewing schedule tells the whole story of why interstellar objects make poor case studies for defending Earth. They appear out of nowhere, linger for a short period, then vanish forever. In contrast, the asteroids bound to the sun return on predictable timelines. They give us multiple chances to observe, measure, and refine models of their orbits. They are the reliable residents whose paths can be charted and anticipated, unlike the one-time tourists who streak through and disappear into the void. So while it's worth marveling at the show 3i Atlas provides, appreciating the technology that lets us detect an object from beyond our star system, and acknowledging the global collaboration that makes such observations possible, we mustn't lose sight of where the real work happens. Planetary defense isn't about chasing spectacular visitors. It's about patiently cataloging the everyday asteroids, the ones bound to stable orbits, the ones circling with us for millions of years. Because while we gaze at the dazzling traveler that poses no real danger, countless others quietly continue their elliptical journeys, some coming uncomfortably close to Earth's path. This leads to a shift in perspective, reframing risk between known neighbors and rare visitors. The universe plays by simple rules, but humans often interpret them backward. Familiarity should make us feel safe, yet it also tempts us into ignoring the dangers closest to home. The real threats aren't the mysterious outsiders from deep space. They are the asteroids we share this solar neighborhood with, predictable, chartable, but still capable of immense destruction if their paths line up with ours. To understand what matters, astronomers use a clear taxonomy. Near-Earth asteroids, or NEAs, are defined by one condition: their orbits carry them within 1.3 astronomical units of the Sun, about 200 million kilometers, close enough to intersect Earth's orbital path. Within this category are 4 families: sorted by how their orbits behave. The Aitons spend most of their time inside Earth's orbit, circling closer to the Sun, but their stretched paths cross ours at points. The Apollos are more numerous, with orbits that extend beyond Earth's but cut through our trajectory as they loop back. The Amals usually stay just outside Earth's orbit, but their closest approaches still bring them near our neighborhood. Finally, the Aiteras orbit entirely inside Earth's path, yet a few can still swing outward enough to approach us at their farthest distances. Within these groups lies a smaller, more concerning subset, the potentially hazardous asteroids, or PHAs. The definition sounds technical, but the idea is simple. They're large enough to cause devastating damage, and their orbits bring them uncomfortably close to Earth. Specifically, a PHA has an orbital path that comes within about 7.5 million kilometers of our planet, and a brightness level corresponding to a body at least 140 meters across. That size isn't chosen at random. An impact from something that large could obliterate a major city and alter regional stability for years. These are not the world-ending monsters kilometers wide, but they are city killers, disasters capable of ending millions of lives and reshaping society. History has already given us a taste of what small ones can do. In 2013, the Chelyabinsk meteor exploded in the atmosphere over Russia. It was barely 20 meters across, yet it released a shockwave powerful enough to injure over 1,500 people and damage thousands of buildings. Now multiply that destructive power by 7 in size, and the outcome changes from widespread injuries to outright catastrophe. NASA has assured us that for the next century, no known large asteroid is on a collision course with Earth. That's comforting, but it only applies to the specific objects we've already tracked. The wider population of PHAs includes over 2,000 identified members, and that number keeps growing as new surveys expand our reach. Every discovery represents another roll of the cosmic dice, another potential date with chance alignment in some future century. The history of asteroid detection shows how rapidly our awareness has grown. In 1990, astronomers had logged fewer than 200 NEAs. By the year 2000, that total had surpassed 1,000. Today, the catalogue contains more than 34,000, with roughly 3,000 new ones being added each year. The biggest, those a kilometer or more in size capable of causing global-scale damage, are mostly accounted for. Astronomers estimate we've identified more than 90% of them, and none pose any immediate threat, but the mid-sized bodies, the 100 to 500 meter range, are still mostly undiscovered. Tens of thousands are believed to exist, each capable of erasing a region the size of a country if one were to strike. Efforts to close that gap are underway. The upcoming NEO Surveyor mission, an infrared telescope designed specifically for asteroid hunting, promises a leap forward in detecting the dark, difficult-to-spot objects that ground-based instruments miss. Its launch, scheduled no earlier than late 2027, should dramatically improve our view of this hidden population. Meanwhile, the statistics reveal both comfort and unease. On any given day, several small near-Earth asteroids pass within the Moon's orbit. These close brushes are so common that NASA runs automated systems to calculate and post their paths without human involvement. The near misses don't always make headlines, but they remind us that Earth is not isolated in space. It moves through a crowded neighborhood of rocky companions, and the difference between a safe flyby and a devastating impact can be measured in mere thousands of kilometers. Most of the small objects that pass near us are harmless, burning up in the atmosphere long before they can cause any real damage. But every so often something larger slips through undetected, reminding us just how incomplete our monitoring really is. The pattern of these near misses highlights an important truth about asteroid risk. It isn't about whether one specific rock is dangerous, it's about the long game. Each individual pass carries only a tiny chance of collision, but stack up thousands of those passes over decades, centuries, and millennia, and those odds become far less comforting. What looks safe today may not stay that way forever. That's exactly why using something like 3i Atlas as a model for planetary hazards misses the point entirely. Because of its hyperbolic path, Atlas is on a one-way trip through our system, untouched by the gravitational nudges that slowly reshape the orbits of bound asteroids. It will never circle back, never creep closer on each pass, never evolve from harmless curiosity to looming threat. Its story ends after this brief visit, But near-Earth asteroids don't disappear. They keep coming back, their trajectories tugged by the planets, especially by giants like Jupiter, making small changes that over time can shift them from benign neighbors into dangerous intruders. On top of that gravitational influence, there's another subtle but powerful force at play, the Yarkovsky effect. First described by a Russian engineer over a century ago, this phenomenon happens when sunlight heats one side of an asteroid, and that heat is released as radiation hours later, after the asteroid rotates. This uneven emission acts like a tiny engine, pushing the asteroid ever so slightly. The push is weak but relentless, and over thousands of years it can shift an asteroid's path enough to make the difference between a safe pass and a catastrophic collision. Tracking something like that isn't easy. Detecting the Yarkovsky effect requires years of precise measurements, carefully recording the asteroid's position against background stars and looking for the tiniest drifts in its orbit. It's the kind of slow, methodical science that only makes sense for objects that will be around long enough to matter. That's why it doesn't apply to interstellar visitors like Atlas. But it's absolutely critical for near-Earth objects, the ones that keep coming back again and again. And here's the paradox. The work that matters most rarely makes headlines. There's no drama in watching astronomers take thousands of measurements, refine orbital models, and carefully track faint points of light year after year. It doesn't sound as exciting as announcing the discovery of a visitor from another star system. But this steady, unglamorous accumulation of knowledge is exactly what will allow us to spot the real dangers in time to do something about them. Compare that to Atlas. For a few months it commands the world's attention. Scientists publish papers, news outlets rush to cover it, and the public imagines interstellar mysteries and alien chemistry. Then it's gone, never to return. Meanwhile, teams around the world dedicate their careers to the slow grind of studying the asteroids that will be here long after Atlas has vanished. They measure, recalculate, refine, and repeat, work that could one day mean the difference between a safe Earth and a global disaster. There's an irony in how much excitement interstellar objects generate. In a way, our fascination with them proves how successful our planetary defense systems have become. We can afford to treat a comet like 3I Atlas as nothing more than a scientific curiosity precisely because astronomers have already built the networks, the telescopes, and the computational tools to separate spectacle from genuine danger. That safety net exists thanks to decades of persistence. Previous generations of researchers took the ordinary threats seriously, even when the public and the media weren't interested. They built the global databases of near-Earth asteroids, developed software capable of projecting their orbits centuries into the future, and set up international collaborations so data could be shared in real time. They knew the real danger wasn't in the once-in-a-lifetime visitor, but in the countless neighbors we see all the time but don't fully understand. And that brings us to one of the most dramatic examples of all the asteroid, that forced the world to rethink how it communicates risk, how it calculates uncertainty, and how it separates headlines from reality. This was the object that for a brief moment carried the highest recorded chance of colliding with Earth. Its story highlights everything we've been discussing, the difference between scary but irrelevant interstellar travelers and the genuine threats posed by near-Earth neighbors. That asteroid's name is Apophis, and its journey from terrifying prospect to scientific breakthrough tells us everything about how planetary defense really operates. The story began on June 19th, 2004, at the Kitt Peak National Observatory in Arizona. Astronomers Roy Tucker, David Tholen, and Fabrizio Bernardi were running a routine survey for near-Earth objects when they noticed a faint point of light shifting slightly against the star field. At first glance, it seemed unremarkable, just another entry in the growing catalogue of space rocks. But further analysis revealed this tiny speck was moving along a path that would soon make it the most closely watched asteroid in human history. Initially labeled 2004 MN4, it would later be renamed Apophis, after the ancient Egyptian serpent deity symbolizing chaos and destruction. The choice of name turned out to be unsettlingly appropriate. Early calculations based on just a few nights of data suggested something unprecedented. This asteroid wasn't on a comfortable orbit around the Sun. Instead, it appeared to be heading toward a potential impact with Earth, with April 13th, 2029, standing out as the possible date of collision. The numbers were alarming. Initial estimates suggested nearly a 3% chance of impact, by far the highest probability ever calculated for a known asteroid. By December of that year, the estimates had narrowed to about 2.7%. That may sound small, but in astronomical terms it was huge, enough to propel Apophis into the global spotlight. The date only amplified the unease. Friday the 13th, April 2029. An asteroid named after the god of chaos, threatening Earth on one of the most ominous dates in human superstition. It almost seems scripted. This probability rating translated to a level 4 on the Torino Impact Hazard Scale, a system running from 0, meaning no risk, to 10, meaning certain global catastrophe. No object had ever scored that high before. A level 4 doesn't mean the end of civilization, but it does demand urgent and serious observation. Suddenly, what had started as a routine detection became an international priority. Observatories worldwide turned their telescopes toward Apophis, racing to collect as much data as possible. Each new measurement refined its orbit, helping to determine whether the nightmare scenario of 2029 was real or just a false alarm. When Apophis was flagged as a possible danger, tracking it became a top priority for agencies worldwide. The European Space Agency quickly pushed its Space Situational Awareness program to monitor it, while NASA expanded its Near-Earth Object program, pouring resources into fresh observations and detailed analysis. What unfolded over the following months perfectly demonstrates why asteroid risk assessments are a marathon, not a sprint, and why early terrifying numbers should never be mistaken for the final word. New data revealed that Apophis wasn't just any rock in space. It belongs to the S-type family, meaning it's made of stony material mixed with nickel and iron. It's shaped like a stretched-out potato, roughly 340 meters long and 150 meters wide. Its surface is unusually dark, bouncing back only about 23% of the sunlight it receives. That dim reflection made it far harder to spot, despite its intimidating size. Radar scans from both the legendary Arecibo Observatory and the Goldstone Complex gave scientists clearer views of its spin, its rugged shape, and its rocky terrain. Those size measurements carried heavy implications. A body this large slamming into Earth at typical asteroid speeds would unleash energy on the scale of hundreds of megatons of TNT, about 10 times more powerful than the largest nuclear weapon ever detonated. While not an extinction-level blow like the Chicxulub impact that wiped out the dinosaurs, it would still be catastrophic on a national scale, killing millions and shaking the global economy for years. Yet those frightening numbers sidestepped the most basic question: was Apophis actually on course to strike Earth? With every new observation, uncertainty in its predicted orbit tightened. The key breakthrough came when Don Yeomans and his team at NASA's Jet Propulsion Laboratory dug into old sky surveys. They discovered that Apophis had actually been photographed years before its official discovery, just hiding as a tiny, unidentified speck among the stars. By pulling that archival data from as far back as March 2004, they dramatically extended the observation window, giving them a much clearer picture of its future path. Slowly, confidence grew. NASA eventually confirmed what everyone hoped to hear. Earth was safe from Apophis for at least the next century. But that level of reassurance didn't happen overnight. It took years of painstaking measurements, and the 2005 observing window, when Apophis was best positioned for telescopes, was especially critical. Those data points finally ruled out the chance of a 2029 collision. By 2006, calculations showed the impact probability had shrunk to virtually zero. Yes, Apophis would pass very close to Earth on April 13th, 2029. Closer than our own geostationary satellites, at a distance of just 32,000 kilometers. But close is not impact. The planet, its inhabitants, and even satellites in orbit would remain unharmed. Still, the asteroid remained a hot topic among scientists for another reason: gravitational keyholes. A gravitational keyhole is a tiny patch of space, sometimes only a few hundred meters wide, that acts like a cosmic trapdoor. If an asteroid happens to pass through one during a close flyby, Earth's gravity can nudge its orbit just enough to set it on a collision course years or decades later. For Apophis, one keyhole was linked to a potential impact in 2036, and early projections couldn't entirely dismiss the possibility. Even after the 2029 threat was gone, the shadow of 2036 lingered. Solving that puzzle required tracking an even subtler effect, the Yarkovsky effect. This is the slight push an asteroid experiences, because it absorbs sunlight, heats up, and then re-radiates that heat unevenly into space. The push is tiny but relentless, causing an orbital drift over years. Detecting it required incredible precision, measuring Apophis's position against background stars to within hundredths of an arc-second. Finally, in 2021, independent teams confirmed it. Apophis was indeed drifting, sliding by about 70 meters per year due to the Yarkovsky effect. That shift was enough to rule out the 2036 keyhole, erasing the last thread of worry for more than a century. This journey, from panic to certainty, shows how planetary defense is supposed to work. Early observations with huge uncertainties produce scary probabilities. As more data pours in, those uncertainties shrink until the risk can be eliminated with confidence. Apophis never stopped being dangerous in theory. It's still a massive rock that comes uncomfortably close to our planet, but it ceased to be a specific date threat once its orbit was mapped with precision. The difference between vague danger and a genuine countdown is nothing more than the accuracy of the math. This saga also shows how asteroid warnings should be communicated. That first 2.7% impact chance wasn't a false alarm. It was simply the best estimate with limited information. As scientists refined their data, the risk dropped steadily towards zero. What once looked like an inevitable disaster transformed into an opportunity for science. Now, instead of fearing it, astronomers are preparing for a show. On April 13th, 2029, at 21:46 UTC, Apophis will sweep past Earth at just 31,600 kilometers above the surface. For context, that's 10 times closer than the Moon, and closer than many satellites we rely on every day. What was once labeled a potential doomsday has turned into one of the most precisely predicted astronomical spectacles in human history. And the story doesn't end here. In fact, the most thrilling chapter is still ahead. Apophis's safe but breathtaking 2029 flyby will be the closest encounter with an asteroid of its size ever recorded in modern times, threading the space between Earth and the geosynchronous satellite belt. Far from a threat, it has become an event that could reshape how humanity studies, understands, and even defends against cosmic intruders. The date of April 13th, 2029 has already carved its place in history. It falls on a Friday the 13th, a date usually tied to superstition, but this time remembered for science. On that night, if skies are clear and you happen to be in the right regions, parts of Europe, Africa, or Western Asia, you may look up and, without a telescope, spot a star-like point racing across the heavens. That point won't be a satellite or an aircraft. It will be Apophis, a 340-meter-long mass of rock and iron, visible to the naked eye for the very first time since its discovery more than 2 decades earlier. But visibility is only the surface of what makes this encounter extraordinary. At such a close distance, Earth's gravity won't just tug on Apophis, it will actively reshape its future. This isn't merely an astronomical event to watch, it's a live experiment in celestial mechanics, unfolding in real time before a worldwide audience of scientists and skywatchers alike. As Apophis passes through Earth's neighborhood, our planet's gravitational pull will squeeze and stretch the asteroid in subtle but powerful ways. These tidal forces are similar to what the Moon does to Earth's oceans, but compressed into just a few hours. For Apophis, the result may be seismic changes, not quakes like those we feel on Earth, but stress-induced tremors across its surface that could trigger landslides, rearrange loose debris, and possibly alter its spin. Right now, Apophis rotates once every 30.6 hours, a slow tumble. Yet during the flyby, Earth's gravity could either accelerate or slow that spin, depending on how its elongated shape and interior mass interact with the pull of gravity. The asteroid's internal makeup is the biggest wildcard. Many space rocks aren't single solid chunks of stone. Instead, they're rubble piles, a fragile mix of dust, gravel, and boulders clumped together by weak gravity. Imagine a loosely packed bag of pebbles floating in space. When tidal stress acts on something like that, the response can be dramatic. If Apophis is more solid like fractured bedrock, it might leave the flyby relatively unchanged apart from its orbit and spin. But if it's a rubble pile, Earth's tug could cause surface collapses, exposing raw material that has been shielded from sunlight and cosmic weathering for millions of years. The most intense stress will peak at 21:46 Universal Time on April 13th, the exact moment Apophis swings closest to our planet. In that instant, Earth's gravity will pull on it with a force about 50 times stronger than its own self-gravity. For a loose rubble pile, that's a brutal test of structural integrity. Astronomers won't just be spectators. Ground-based radar will be crucial in documenting what happens. California's Goldstone Solar System radar and the Green Bank Telescope in West Virginia are capable of imaging the asteroid with meter-level resolution, capturing details about its surface texture, boulders, and any changes caused by tidal stress. Optical telescopes worldwide will measure brightness and color shifts, which could signal freshly exposed material on the surface. If landslides do occur, those subtle changes in reflected light will provide direct evidence. Meanwhile, projects like the Catalina Sky Survey and the Linear program will precisely track variations in Apophis's spin rate and axis orientation. Even tiny adjustments in these properties could unlock valuable insights into its inner structure and strength, knowledge that could prove vital if humanity ever needed to deflect a similar object in the future. Beyond science, this encounter carries massive potential for public engagement. Unlike most celestial events that demand telescopes, perfect darkness, or special timing, Apophis will be bright enough for ordinary people to witness with their own eyes. Amateur astronomers across continents are already preparing global observation campaigns. The International Astronomical Union's Minor Planet Center plans to collect reports from both professionals and hobbyists, stitching together a worldwide record of how Apophis behaves during its closest pass. Schools and universities are also gearing up, weaving Apophis into lesson plans on gravity, orbital mechanics, and planetary defense. For once, topics like tidal forces and orbital dynamics won't just be abstract equations in a textbook. They'll be demonstrated live in the night sky, visible to students, families, and entire communities. Satellite operators are preparing as well. While the asteroid won't actually strike any satellites, it will skim through the region where many geostationary spacecraft orbit. That means constant monitoring and, if necessary, small adjustments to satellite operations. The European Space Agency has already committed to treating the flyby as a real-world rehearsal, a way to test space situational awareness strategies that could also apply to managing orbital debris. Even climate scientists are curious. Though Apophis will remain well above Earth's atmosphere, its close passage might cause tiny, barely measurable ripples in the density of the upper atmosphere. Detecting them will be difficult, but the possibility is intriguing enough to warrant attention. And the timing couldn't be better. By 2029, humanity will likely have multiple missions on Mars, active lunar bases or orbiters, and a fleet of powerful space telescopes. These spacecraft could offer perspectives on Apophis from across the solar system, giving us a multi-angle view of this one-of-a-kind event. The flyby will mark a turning point. Apophis will no longer be remembered as the asteroid that once threatened Earth, but as a natural laboratory for testing our understanding of asteroid physics under extreme conditions. Every observation, every model, and every piece of data gathered in 2029 will help refine our planetary defense strategies for the future. If we ever discover another asteroid with similar characteristics, and odds are we will, the knowledge gained from Apophis could determine how prepared we are to respond. And here's the most exciting part. We won't just be watching from observatories on Earth. Sometimes the universe seems to align in ways that feel almost intentional. As Apophis prepares for its once-in-history close pass in 2029, NASA has arranged for one of its most capable spacecraft to be waiting. The mission is called OSIRIS-APEX, and its story shows just how seriously scientists are treating this extraordinary opportunity. OSIRIS-APEX wasn't originally built for Apophis. It began its life as OSIRIS-REx, the spacecraft that spent years orbiting the asteroid Bennu, collecting priceless samples, and safely delivering them back to Earth in 2023. Most missions would have ended there, retired after success. But instead of shutting it down, NASA gave it a new purpose, redirecting it to Apophis. This creative repurposing turned a proven explorer into the centerpiece of what could become the most detailed asteroid study ever attempted. The spacecraft is scheduled to meet Apophis in June 2029, about 2 months after the asteroid's dramatic pass by Earth. That timing is deliberate, close enough to observe any fresh changes caused by tidal stress, yet distant enough to ensure the spacecraft can safely operate around a potentially altered object. Once it arrives, OSIRIS-APEX will spend nearly a year and a half studying Apophis in exquisite detail. Its objectives sound like a wish list for planetary defense. The top priority is to measure exactly how Earth's gravity altered the asteroid, its orbit, spin, and orientation. Ground-based telescopes will already provide rough answers, but OSIRIS-APEX can deliver precision. It carries cameras and sensors capable of resolving features down to centimeters. That means scientists will see whether boulders shifted, landslides occurred, or surface patterns changed during the flyby. Its thermal spectrometer will map temperatures across Apophis's skin, searching for heat signatures that might reveal fresh material exposed from below. But the mission goes further. Engineers have planned a maneuver, unlike anything tried at Bennu. The spacecraft will descend to within just a few dozen meters of Apophis's surface and fire its thrusters, deliberately kicking up dust and rock. Unlike its predecessor, OSIRIS-APEX doesn't have a sampling arm, so it won't grab material. Instead, this blast will allow instruments to analyze newly disturbed regolith from afar. It's a bold experiment, one that carries risk but could reveal layers of the asteroid that sunlight and cosmic radiation have never touched. Operating that close to an asteroid that just underwent tidal stress is no simple task. If Earth's pull caused significant reshaping, then Apophis might present an unstable, unpredictable environment. Before attempting close approaches, the spacecraft will first need to map the asteroid's new gravitational field, rotation, and terrain. So navigation around a body like Apophis is already challenging. Its stretch shape and spin create a lopsided gravitational field. If the flyby altered its motion, mission controllers will have to adapt quickly, rewriting plans on the spot. The potential rewards are enormous. By comparing ground-based data collected before the flyby with OSIRIS-APEX's detailed surveys afterward, scientists will gain an unprecedented look at how asteroids react when yanked by a planet's gravity. That knowledge directly informs planetary defense strategies. If humanity ever needs to nudge a threatening asteroid away from Earth using a spacecraft or impactor, we'll need to know exactly how such bodies respond to sudden forces. OSIRIS-APEX will provide the real-world evidence to test and refine those models. From an engineering perspective, the mission is already a triumph. By the time it reaches Apophis, OSIRIS-APEX will have been operating in space for over 10 years, far beyond its original design life. Extending its career demonstrates how spacecraft can be repurposed for multiple targets, multiplying the value of each mission. It sets a precedent for future asteroid explorers to shift from one object to another, building a chain of knowledge across decades. The effort isn't just about one spacecraft. Ground observatories, radar facilities, and orbiting telescopes will all be coordinating with OSIRIS-APEX. Together, they'll produce the richest, most comprehensive data set ever gathered for a single asteroid. This level of cooperation ensures no detail is missed, no measurement overlooked. Timing is everything. Arriving in mid-2029 means Apophis will have moved far enough away from Earth to avoid interference from our planet's gravity, yet still close enough for fast, reliable communication with mission control. During its 18-month study, the spacecraft will observe the asteroid under varying lighting and angles, capturing how it behaves in different conditions. The focus will be on questions that directly matter for defending Earth. How rough is its surface, and how are boulders distributed? That determines how momentum transfers if we ever need to strike it. What does its internal structure look like, and how strong is it? That tells us how it would react to a push or pull from a deflection attempt. What is its thermal behavior? That affects how sunlight and heat slowly shift its orbit through the Yarkovsky effect. The thruster experiment deserves special mention. By actively disturbing the surface, OSIRIS-APEX will simulate what happens when external forces act on an asteroid. If the material is loose and easily scattered, that has big implications for future deflection methods. Knowing whether the surface clings together or collapses easily could mean the difference between a successful planetary defense strategy and a failed one. Perhaps the most important lesson from OSIRIS-APEX is that asteroid missions don't have to be single-use. What started as a mission to study Bennu has transformed into a planetary defense experiment. It bridges pure science with practical application, showing how exploration and protection can work hand in hand. With Apophis as its new target, this spacecraft will not only teach us about one asteroid, but could provide the blueprint for protecting Earth from the next one. The OSIRIS-APEX mission isn't just about Apophis itself, it's also paving the way for the future of asteroid rendezvous missions in an era where planetary defense is no longer science fiction but an active necessity. As new near-Earth objects continue to be catalogued, space agencies may face moments where a potential threat is identified and rapid response missions must be launched. The experience gained from APEX navigating and studying Apophis will act as a training ground for designing and executing those fast turnaround missions in the years ahead. Beyond its scientific objectives, this mission has the potential to captivate the public like few others. Unlike distant or obscure targets that only astronomers follow, Apophis will already be a household name by 2029 after its widely covered flyby. When the spacecraft begins its close-up investigation afterward, it won't just feel like a new mission, it will feel like the continuation of a story everyone is already watching unfold. This connection ensures public interest in asteroid research and planetary defense won't vanish once the flyby headlines fade, but instead will deepen as fresh discoveries come in. The data APEX collects could fundamentally reshape how we calculate asteroid risks. At present, impact assessments rely heavily on statistical models that use limited observations and assumptions about asteroid properties. But APEX's close encounter with Apophis will deliver precise, ground-truth measurements that can correct and refine those models for decades to come, making predictions about future threats more reliable than ever. Yet even as engineers prepare APEX for its post-flyby encounter, the larger story of planetary defense has another lesson to offer, one that goes back to how Apophis first burst into the headlines. Its journey from being labeled a potential doomsday rock to a scientific opportunity shows how fragile our early predictions can be, and why understanding the difference between danger and uncertainty is absolutely critical. This lesson began nearly 2 decades earlier, on December 27, 2004. On that day, Stephen Chesley at NASA's Jet Propulsion Laboratory ran orbital calculations for a recently discovered asteroid, still designated 2004 MN4. The numbers he got were alarming. Based on only 74 observations spanning just over 2 months, the asteroid, later named Apophis, appeared to have a 2.7% chance of colliding with Earth. On April 13, 2029, that number may not sound large at first, but in asteroid terms, it was extraordinary. For perspective, the odds of a person being struck by lightning in their entire lifetime are about 1 in 15,000 or 0.007%. Compared to that, Apophis looked more than 300 times as likely to hit our planet than lightning is to hit you. This probability earned Apophis a level 4 ranking on the Torino scale, the first time a real asteroid had ever been rated that high. Developed by MIT's Richard Binzel and introduced at a 1999 conference in Turin, Italy, the Torino scale measures impact threats on a scale from 0 to 10. Almost all asteroids are classified as 0, meaning no danger at all. Apophis, however, briefly reached level 4, signifying a close approach with a measurable chance of causing regional destruction. But here's where the nuance was lost in headlines. The 2.7% was never a prediction of disaster, it was a reflection of how uncertain the data still was. Early orbit calculations are notoriously shaky because they're based on such short observation arcs. Imagine throwing a baseball and then trying to predict its landing spot after watching it for just a fraction of its flight. You'd almost certainly be wrong. Even if the physics is flawless, the problem is compounded with asteroids, since their paths are shaped by gravitational nudges that stretch across millions of years. Each observation, marking an asteroid's position against the background stars at a precise moment, shrinks the uncertainty a little. But with only a few dozen measurements over a short time frame, the possible future positions remain spread across a wide region of space. For Apophis, those 74 early observations simply weren't enough to pinpoint its exact orbit. That infamous 2.7% wasn't saying Apophis will probably hit Earth, but rather, we don't yet have enough information to say it won't. Adding to the uncertainty were the so-called gravitational keyholes. During its close pass in 2029, Earth's gravity would bend Apophis's trajectory slightly. If the asteroid happened to pass through a tiny corridor of space, a keyhole only a few hundred meters wide, it could be nudged onto a collision path for a later date. In Apophis's case, one keyhole was calculated to set up an impact in 2036. At just 610 meters across, smaller than a city block, it was minuscule in cosmic terms, but still large enough that early calculations couldn't dismiss the possibility of Apophis threading the needle. This intersection of orbital mechanics and public communication created confusion. News outlets seized on the dramatic 2.7% figure, while glossing over the uncertainty that produced it. To the average person, it sounded like a prediction of doom. Astronomers, however, knew the real story. With more data, the impact odds would either shrink towards zero or solidify into a genuine threat. Statistically, it was almost always the former. Most so-called killer asteroids are eventually downgraded once the orbital data improves. The key was to keep observing. The effort that followed was unprecedented. Observatories worldwide began tracking Apophis every chance they got, adding new points of data to refine its orbit. Radar facilities measured distances with incredible precision. Space-based telescopes supplied observations unaffected by Earth's atmosphere. Then came a breakthrough. Astronomer Don Yeomans and his team realized they could extend Apophis's timeline backward by digging into archived sky survey images. By combing through data taken before the asteroid was officially discovered, they found earlier sightings dating back to March 2004 that effectively doubled the length of its observational arc, drastically tightening the orbital calculations. The recovery data turned the tide. With a longer observation arc and hundreds of new position measurements added, the uncertainty surrounding Apophis's orbit shrank dramatically. By the end of 2005, refined models showed that the asteroid posed no threat for its highly anticipated 2029 encounter. Yes, it would skim past Earth closer than any other object of its size in recorded history, just 32,000 kilometers away, nearer than some satellites. But it would miss us. That confirmation erased the nightmare scenario of a 2029 collision, but the story wasn't finished. There was still the question of the 2036 window. Apophis would pass close enough to Earth's gravitational keyhole in 2029 that, with uncertainties still lingering, astronomers couldn't yet give a definitive all-clear for its later return. For years after, a sliver of risk remained, tiny but not zero. To settle the matter, scientists needed to measure something subtle yet powerful, the Yarkovsky effect. This is the slow orbital drift caused when an asteroid absorbs sunlight and re-emits it as heat. A force so faint you'd never notice it on Earth, but strong enough over centuries to shift the path of a mountain-sized rock through space. Detecting it requires years of ultra-precise measurements. That breakthrough arrived in 2021. Independent research teams confirmed that Apophis was drifting at a rate of about 70 meters per year along its orbit. That might not sound like much, but it was decisive. The measured drift showed the asteroid would completely avoid the 2036 keyhole, ruling out any threat for more than 100 years. NASA declared with confidence that Apophis poses no danger to Earth for at least a century, a rare instance where a negative prediction is celebrated as one of the most solid conclusions in planetary science. This evolution from a 2.7% chance of impact to a definitive all-clear is a textbook example of how planetary defense should work. Initial warnings spark urgency. Observations multiply. Precision improves. Uncertainty collapses into certainty. The Apophis case became the blueprint for how to handle future threats. Treat early numbers as provisional, emphasize uncertainty when communicating with the public, and keep gathering data until the truth becomes clear. Media outlets, too, learned a lesson. Early figures shouldn't be reported as doomsday prophecies, but as placeholders waiting to be corrected with time. Just as important as the math was, the global collaboration. NASA's Planetary Defense Coordination Office, the European Space Agency's monitoring programs, and observatories around the world pooled their observations to refine Apophis's orbit. That international network, first tested on Apophis, is now the standard model for dealing with new potential threats. Perhaps the biggest takeaway from the scare was learning to separate statistical uncertainty from actual danger. The original 2.7% wasn't a warning that the end was near. It was a sign that astronomers didn't yet have enough information to dismiss the possibility. That distinction is crucial. Confusing those two concepts could lead to panic, poor policy choices, or miscommunication between scientists and the public. In the end, Apophis transformed from a feared harbinger of destruction to a scientific gift, an event that will inspire curiosity, research, and even public stargazing when it streaks across the sky. The system worked. Early alarms pushed astronomers to dig deeper. The data improved, the danger faded, and Earth breathed easier. But the what-if still lingers. What if the story had gone the other way? What if more observations had confirmed the threat instead of removing it? What would humanity be facing if Apophis or an asteroid of similar scale were truly on course for a collision with Earth? Picture the date, April 13th, 2029. Instead of a safe pass, a 340-meter-wide body of rock, mixed with nickel iron, is barreling toward Earth at roughly 25 kilometers per second. The sheer energy of such an impact would exceed 500 megatons of TNT, 10 times more powerful than the Soviet Tsar bomber, the largest nuclear device ever detonated. But those raw energy numbers only scratch the surface of what such an event would mean. The consequences would depend heavily on where the asteroid struck: land or ocean, crowded city or barren plain, shallow waters or the deep Pacific. Each scenario writes its own chapter of catastrophe. On land, the collision would gouge a crater 4 to 5 kilometers wide, with the blast instantly vaporizing everything within several kilometers of ground zero. For a fleeting moment, temperatures at the site would rival the surface of the sun. A fiery ball expanding 15 kilometers across would ignite everything flammable within hundreds of square kilometers, erasing life and structures alike. Though that initial inferno would only be the opening act. The shockwave racing outward at supersonic speeds would flatten buildings, forests, and infrastructure up to 50 kilometers from the impact point. Earth itself would ring with seismic waves strong enough to be measured across the globe. Above, a plume of pulverized rock would billow into the stratosphere, spreading out to darkened skies for months or even years, disrupting agriculture and reshaping climate. If the strike occurred in the ocean, the disaster would unfold differently, but no less violently. Water, at those cosmic speeds, doesn't cushion the blow. It behaves more like solid rock. Millions of tons would vaporize in an instant, creating a colossal steam explosion. The impact would displace unimaginable volumes of water, sending tsunamis racing across entire oceans. Depending on depth and location, waves could reach 10 to 20 meters high, slamming into coastlines thousands of kilometers away. The 2004 Indian Ocean tsunami, generated by a massive undersea earthquake, killed over 230,000 people across 14 countries. An Apophis-class impact in the ocean could create waves far larger, with devastation extending across far more densely populated regions. For perspective, remember the Chelyabinsk event of February 15th, 2013. The Chelyabinsk meteor of 2013 was only about 20 meters across, 60 times smaller in volume than Apophis. Yet even that relatively tiny space rock injured more than 1,500 people, shattered windows across a vast region, and caused millions of dollars in damage. It proved a sobering point. Even small asteroids can wreak havoc when they arrive unannounced. Now scale that up from 20 meters to Apophis's 340-meter bulk, and we leave the realm of broken glass and startled residents. What we're facing instead is a regional collapse of civilization, millions of casualties, trillions in economic losses, and aftershocks that would ripple across the planet for decades. While not large enough to trigger the kind of global extinction event caused by the Chicxulub asteroid that ended the dinosaurs 66 million years ago, an Apophis-class impact would still profoundly disrupt life on Earth. Dust and debris lofted high into the stratosphere could cool global temperatures by 1 to 2 degrees Celsius for several years. That may sound small, but it would be enough to disrupt agriculture worldwide and threaten food security for billions of people. And in today's hyper-connected world, the chaos wouldn't stay confined to the strike zone. Supply chains would fracture, financial markets would convulse, and regional collapse could cascade into a global economic crisis. We've already seen how even localized disasters can ripple outward. The 2011 Tohoku earthquake and tsunami in Japan didn't just devastate a nation, it disrupted global manufacturing and shipping for months. Now imagine a catastrophe, an order of magnitude greater. An Apophis impact wouldn't just be a natural disaster, it would be a planetary crisis. The psychological shock could be as devastating as the physical consequences. Unlike earthquakes, hurricanes, or floods, an asteroid impact carries an existential weight. It's a reminder that Earth is not isolated, that cosmic bombardment is still part of our reality, and that survival depends on our ability to anticipate and respond. That awareness alone would leave an imprint on human culture for generations. Emergency response planning shows just how ill-prepared we are. Our systems are built for familiar hazards, storms, quakes, wildfires, events with patterns we understand, and regions we can usually evacuate. But an asteroid strike of this magnitude would leave vast areas uninhabitable for decades, requiring permanent relocation of entire populations. We're talking about moving millions of people, not for days or weeks, but forever. No single nation has the resources to manage such a crisis. True survival would demand unprecedented international cooperation. And the price tag? Unimaginable. The 2011 Japanese tsunami caused about $200 billion in damage. Hurricane Katrina in 2005 inflicted more than $125 billion in losses. An Apophis-class impact could surpass $1 trillion easily. And that doesn't even account for long-term climate disruptions, food shortages, and economic collapse. This is why planetary defense is no longer science fiction. It's policy. Risk experts call scenarios like this low probability, high consequence. The odds of such an impact in any given year are tiny, but the destruction would be so enormous that we can't afford to ignore it. And that brings us back to the contrast between Apophis and 3 Atlas, the interstellar comet that grabbed headlines worldwide. Atlas, despite its dramatic origins, poses zero danger. Its hyperbolic orbit means it will never return, never cross paths with Earth. Apophis, on the other hand, was a real concern precisely because it crosses Earth's orbit. Observations eventually ruled out an impact for the next century, but it remains part of the potentially hazardous asteroid family, objects big enough and close enough to matter. The difference couldn't be starker. Atlas dazzles because it's rare and beautiful. Apophis demands attention because it's ordinary and dangerous. One is a cosmic spectacle, the other is a warning. Which is why scientists caution against being distracted by interstellar fireworks. While the public marvels at harmless visitors like Atlas, the threats that truly matter continue their quiet, elliptical orbits, passing, from time to time, uncomfortably close to the only world we call home. Apophis is set to thread a cosmic needle so precisely that it will skim past Earth at a distance closer than many of the satellites we've carefully placed into orbit. That single fact already tells you everything about why Apophis is a story of consequence, while other so-called sensations in space are little more than distractions. To put it into perspective, Apophis will swing by around 32,000 kilometers from Earth, while communication satellites sit farther out, nearly 36,000 kilometers away. Compare that to 3I Atlas, the interstellar comet that has dominated headlines. It will stay over 8,000 times farther from Earth than Apophis, yet news coverage has focused almost entirely on this visitor from beyond the solar system. The difference isn't just in distance, it's in what these encounters actually mean for human safety. One event is little more than cosmic spectacle. The other is a wake-up call about the thin margin that separates civilization from catastrophe. Why then does the harmless interstellar visitor steal the spotlight? The answer lies in the way our minds process rarity. Apophis may be close, but it's ordinary in composition, just another rocky object of silicate and nickel iron, the kind of material found in thousands of other asteroids orbiting between Mars and Earth. Its path through space was discovered the old-fashioned way, through careful sky surveys, slow data accumulation, and painstaking confirmation. It's nothing exotic, nothing mysterious. nothing that would naturally spark imaginations. By contrast, 3i Atlas is extraordinary simply because of where it came from. It isn't bound to our sun, it's the third confirmed interstellar object to ever be spotted wandering through our neighborhood. The story practically writes itself: a traveler from another star, a mysterious icy body with unknown origins, maybe even whispers of alien technology. Our psychology is wired to chase novelty, so what's truly threatening fades into the background while the unusual seizes attention. But here's the irony. Apophis, in all its supposed ordinariness, is the one that forced planetary defense to grow up. Back in 2004, when early calculations suggested a 2.7% chance it could strike Earth in 2029, the entire astronomical community shifted focus. That probability might sound tiny, but in terms of asteroid impact statistics, it was astronomical. It briefly ranked a 4 on the Torino scale, the highest rating ever given to a real object. Suddenly, telescopes worldwide were working overtime, and risk communication protocols had to evolve on the fly. At that time, NASA didn't even have a dedicated Planetary Defense Coordination Office. Apophis played a direct role in changing that. Europe, too, expanded its space situational awareness program because of lessons learned from the Apophis scare. In short, this so-called ordinary rock reshaped how humanity thinks about monitoring the skies. Now think about 3i Atlas. Has it triggered new global defense strategies? No. Does it require daily monitoring in case it strays too close? Not at all. Beyond scientific curiosity, it has no bearing on planetary defense. Yet it dominates social media feeds and newspaper headlines precisely because it's unusual. And that disconnect between what's fascinating and what's dangerous is where the real danger lies. Every time a story like 3i Atlas breaks, it follows the same pattern. Early reports scream about a visitor from another star. Dramatic renderings flood articles. A glowing comet tail, a mysterious icy core, only later. Buried in technical paragraphs most people skim past are the words "no threat to Earth." The spectacle has already imprinted itself on public imagination. Meanwhile, near-Earth asteroids, the objects that truly matter, rarely get coverage unless there's an immediate threat. Even then, the nuance between probability and certainty is often lost, as the Apophis scare demonstrated. The reality is stark. While the public obsesses over harmless but exotic travelers, the work of cataloguing dangerous asteroids goes largely unnoticed. Over 34,000 near-Earth asteroids have been discovered, but outside of Apophis and perhaps a handful of others, the average person can't name a single one. This imbalance creates a dangerous illusion. The public learns to fear the wrong things and ignore the real threats. When resources get allocated, that distortion matters. If people are more captivated by a comet that will never come near Earth than by a rock that will pass closer than our satellites, political priorities can skew dangerously. Imagine a future scenario where a newly discovered Apophis-class asteroid genuinely threatens impact. If the public doesn't understand the difference between fascinating and dangerous, pressure on policymakers could delay critical decisions. Space agencies know this, which is why they've gotten much more deliberate in communication. Every official NASA statement about 3i Atlas emphasizes one point clearly: it's harmless, no risk, no danger. The comet is spectacular, but irrelevant to human survival. These disclaimers aren't just cautious phrasing, they're backed by precise orbital calculations that leave no ambiguity. That same clarity now surrounds Apophis as well. After years of refining observations and measuring even the subtle Yarkovsky drift, the tiny nudge caused by re-radiated sunlight, scientists can say with confidence that Apophis poses no threat for at least a century. What once looked like a potential civilization ender is now categorized as safe, at least for the foreseeable future. But the key takeaway isn't just that we dodged a bullet, it's that the process worked exactly the way it should. Early alarms based on limited data pushed astronomers worldwide to gather more observations. Those observations shrank uncertainties until probabilities collapsed to zero. This is how planetary defense is supposed to function: quick mobilization, relentless observation, and honest communication of uncertainty. But step back and look at the bigger picture. What does Apophis represent? It embodies the category of objects that demand constant vigilance. near-Earth asteroids with orbits that bring them dangerously close to our planet. These are the ones that matter because they're common, they're local, and they can hit. 3I Atlas, by contrast, represents the category we don't need to lose sleep over. Interstellar objects are fascinating anomalies, but their paths through our solar system are brief, hyperbolic, and one-way. They arrive, they dazzle, and then they're gone forever. The difference between the two categories is crucial when it comes to allocating resources. Every dollar spent obsessing over an exotic comet is a dollar not spent improving asteroid surveys, upgrading radar tracking, or developing deflection technologies. Every hour of telescope time spent photographing a glowing interstellar tail is an hour not spent monitoring the objects that could actually strike Earth. This doesn't mean we shouldn't study 3-eyed Atlas or other interstellar visitors. They offer valuable clues about how planetary systems form and what materials circulate between the stars. But it does mean we need perspective. They are scientific curiosities, not existential threats. When weighed against the mission of protecting Earth, the priorities should be obvious. And that brings us to the year 2029, when Apophis will deliver a once-in-a-lifetime event. While 3I Atlas fades into interstellar darkness never to return, Apophis will glide so close that it will outshine most stars in the night sky. For the first time, scientists will be able to study a potentially hazardous asteroid up close, under controlled conditions, with a global audience watching. The information gathered from this flyby will shape planetary defense strategies for decades. We'll measure its exact size, shape, rotation, and internal structure. We'll test models of how near passes to Earth change orbits. We'll even refine our understanding of how to deflect similar objects in the future. The truth is simple but powerful. Danger isn't measured by how rare or mysterious something is. It's measured by proximity and probability. Apophis is ordinary in composition, but extraordinary in how close it will come. 3I Atlas is extraordinary in origin, but utterly irrelevant when it comes to risk. One deserves fascination, the other demands vigilance. Together, they teach a critical lesson in how we should think about space hazards. When the media runs wild with tales of alien visitors, remember this. The real threats don't come with glowing tales from another star. They come in the form of silent, rocky neighbors that occasionally remind us just how thin Earth's margin of safety really is. On April 13th, 2029, humanity will witness an event unlike anything ever recorded in the history of planetary science. A massive asteroid, Apophis, will glide past Earth at a distance so close that every major observatory across the globe will be locked onto it. This won't just be another routine flyby. It will become the most extensively documented asteroid encounter in human history. A carefully orchestrated campaign that will reveal secrets about the nature of these wandering space rocks and how they respond when confronted by Earth's immense gravity. Across every continent, optical telescopes will aim skyward, chasing Apophis as it streaks across the night sky. Their mission will be to track even the slightest shifts in brightness or subtle color changes on its rocky surface, clues that could expose alterations triggered by the crushing tidal stresses of Earth's pull. At the same time, infrared observatories will monitor variations in heat radiating from its terrain, building thermal maps that may reveal patches of freshly uncovered material never before touched by space weathering. These instruments can detect changes so delicate that even the smallest landslides or exposures of raw rock will stand out against the asteroid's familiar skin. Meanwhile, radio telescopes will step in with a level of detail that borders on science fiction. Facilities like the legendary Goldstone radar in California and the Green Bank telescope in West Virginia will bounce signals off Apophis, generating high-resolution radar images that capture its contours down to scales of mere meters. This means that if Earth's gravitational embrace triggers avalanches of loose material, shifts in boulder fields, or reshaping of its rugged profile, those changes will be visible almost instantly. Planetary scientists will be able to place radar snapshots from 2021 side by side with images from 2029, giving them the first direct comparison of how a near-Earth asteroid transforms under the influence of another world's gravity. Rotation will be another critical focus of study. Today, Apophis turns lazily once every 30.6 hours, slowly presenting different faces to the Sun in a predictable rhythm. But when it sweeps past Earth, tidal forces are expected to disrupt this pattern. The asteroid could spin faster, slow down, or even enter into a chaotic wobble depending on the precise mechanics of the encounter. Measuring these changes requires precision photometry, the careful monitoring of how Apophis brightens and dims as different portions of its surface rotate into sunlight. To achieve this, professional observatories will collect massive datasets, but amateur astronomers will also join the effort. Through coordinated global campaigns, even small backyard telescopes will contribute valuable light curves, proving once again how citizen scientists can play a vital role in shaping planetary defense knowledge. Infrared readings will carry a special kind of importance. Over eons, asteroid surfaces are darkened and reddened by micrometeorite strikes and constant bombardment from solar wind, a slow aging process called space weathering. If Apophis sheds layers of soil and exposes untouched subsurface rock, that fresh material will shine brighter, cooler, and far less red than the weathered exterior we see today. NASA's NEOWISE mission has already built an enormous catalogue of asteroid thermal profiles since 2013, including baseline measurements of Apophis itself. Once the 2029 data is compared, scientists will know if Earth's tidal influence has fundamentally altered its heat distribution or revealed new properties that could never be measured before. Spectroscopy will take the investigation even further. By breaking down the asteroid's reflected light into individual wavelengths, researchers can identify the unique fingerprints of minerals hidden in its crust. If the flyby tears open new surfaces, exposing metallic veins or fresh silicate layers, the differences in mineral abundances will be instantly recognizable. It's like peeling back the layers of a world that has been locked in stone for billions of years, finally exposing what lies beneath. Even space missions not directly observing Apophis will play indirect roles. The European Space Agency's Hera mission, scheduled to be near the Didymos system during the same period, won't have a direct line of sight to Apophis. Yet its state-of-the-art instruments and fresh experience in characterizing small bodies will provide frameworks and comparative models that sharpen the interpretation of Apophis data. What Hera learns about rubble pile dynamics and asteroid cohesion will echo into the 2029 analysis, linking two separate missions into a broader planetary defense tapestry. Perhaps the most intriguing part of the upcoming encounter will be the chance to probe Apophis's interior without physically touching it. And most asteroids are not solid monoliths, but loose aggregates of boulders, dust, and gravel, weakly held together by their own gravity. These fragile rubble piles respond to stress very differently than dense, coherent rocks. If Apophis proves to be tightly bonded internally, Earth's tug may leave only superficial scars. But if it's a fragile heap barely clinging together, the flyby could trigger a cascade of dramatic reshaping events. Understanding which of these outcomes occurs is absolutely critical for planetary defense, because any future deflection attempt will depend on knowing whether we are pushing against a rigid block or a loosely packed cluster of debris. Apophis's elongated form adds another wrinkle. Gravitational tides don't pull evenly. They stretch along one axis while compressing the other. For a misshapen body like this asteroid, the orientation during closest approach will dictate whether the forces elongate it even further or compress it toward a more rounded figure. Models predict that maximum stress will occur precisely at 2146 UTC on April 13, 2029, when Earth's gravity will tug at Apophis with a force nearly 50 times stronger than the asteroid's own self-gravity. To put that in perspective, the tidal pull Earth experiences from the Moon is millions of times weaker compared to our planet's own gravity. Apophis will be tested in a way no asteroid this large has ever been before. The scale of coordination required for this scientific campaign is staggering. Because Earth's rotation constantly shifts the asteroid out of view from different observatories, astronomers on one continent will have to hand off the target to colleagues elsewhere, like a global relay race played out in real time. Data will need to be exchanged quickly and seamlessly, with preliminary findings guiding last-minute adjustments to observing strategies as the encounter unfolds. The margin for error is razor-thin. Light from Apophis will take just 1/10 of a second to reach Earth at closest approach, fast enough for live observation but slow enough that sudden unexpected events could still slip by unnoticed if observers aren't ready. That's why meticulously pre-planned sequences, covering every possible scenario, have already been drafted to guarantee that nothing is missed. What makes this moment truly profound is not just the spectacle of a large asteroid hurtling past our world, but the scientific treasure it offers. For decades, computer models of asteroid interiors and behavior under stress have relied on assumptions, educated guesses about material strength, cohesion, and mechanics. Never before have we had the chance to watch a sizable near-Earth asteroid undergo this kind of extreme gravitational encounter while under the constant gaze of the world's best instruments. Apophis will provide the first real-world validation of these theories. Did we get it right, or are there surprises waiting to upend everything we thought we knew about these wandering rocks? The answers will shape the future of planetary defense. If models prove accurate, our confidence in predicting asteroid responses to deflection attempts will soar. If they fail, the 2029 flyby will highlight urgent gaps in our understanding, gaps that must be closed before humanity faces a genuine collision threat. Either outcome advances knowledge and strengthens our ability to protect Earth. And so, in April 2029, the sky will host more than just a close celestial pass. It will host a turning point, a live experiment written in the language of gravity and rock, observed by the combined eyes of humanity. Apophis will brush past Earth, not as a destroyer, but as a messenger, delivering hard data, shaping strategies, and reminding us that the cosmos is not distant, but immediate. For a brief window, an asteroid will dance at the edge of our world, and in that dance we may discover the keys to safeguarding our future. When scientists look at asteroids, the purpose goes far beyond curiosity or theoretical research. These studies can directly shape how humanity prepares for threats from space. The way an asteroid reacts under tidal stress, for example, tells us how it might respond if we ever try to deflect it with a spacecraft impact or another strategy. If one of these space rocks proves tougher or looser than expected, that knowledge could completely change how engineers design missions to protect Earth. This is why the 2029 flyby of Apophis is being treated almost like a rehearsal. It is more than just a rare astronomical event. The international coordination, instant data exchange, and advanced observation methods being built for that moment could one day be the exact systems humanity relies on if a genuine threat appears. Unlike certain past encounters with other space objects that offered little practical value, Apophis provides real usable information that could guide future planetary defense and even save lives. What makes this story fascinating is not only the asteroid itself, but how humanity has evolved in its response to these cosmic risks. The journey from fear to preparation shows just how far planetary defense has come. When Apophis was first spotted back in 2004, it sparked panic because early calculations suggested it might collide with Earth. At that time, there was no global defense framework. NASA tracked near-Earth objects, but there was no single office dedicated to impact hazards or strategies for mitigation. The European Space Agency studied asteroids too, but it lacked a specific mandate for defense. Around the world, no unified system existed for communication or response if a dangerous object were actually on its way. The Apophis scare changed everything. Just 2 years later, NASA created the Near-Earth Object Observations Program. For the first time, a structured budget and resources were dedicated not only to finding these asteroids, but also to measuring their orbits with high accuracy, to determine actual risks. This step marked the official acknowledgement that defending Earth required long-term, systematic work, instead of rushing to react whenever a threat appeared. Europe followed soon after, launching its own initiative focused on monitoring space dangers. What began as efforts to track debris and space weather gradually expanded to include asteroid detection and defense planning. By connecting observatories and surveillance networks, Europe laid the foundation for its first coordinated defense structure. Still, setting up organizations was only the beginning. The Apophis episode revealed that understanding and redirecting a real asteroid is not simply about spotting it in the sky. You need to know its exact mass, density, surface makeup, inner structure, and even how solid or loose it is. These details determine how it reacts when you try to push it off course. That is why the double asteroid redirection test, launched in late 2021, was such a historic moment. This was humanity's very first real attempt to strike an asteroid deliberately and measure the outcome. Its target was Dimorphos, a smaller asteroid orbiting a larger companion, Didymos. The mission sounded almost like science fiction. Crash a spacecraft into Dimorphos at tremendous speed and then watch if its orbit changes. But what happened exceeded all hopes. On September 26, 2022, the impact shortened Dimorphos's orbit by a full 32 minutes. The mission only needed a 10-minute shift to be considered a win, yet the result was 3 times greater. Even more surprising was the momentum boost effect. Instead of only transferring the force of the spacecraft itself, the impact sprayed debris outward, adding extra push that amplified the orbital shift. Models had suggested this could happen, but no one had ever proven it in space until then. With that single impact, humanity gained its first real calibration data for asteroid deflection, turning theory into fact. This success proved something extraordinary. Given enough warning and planning, crashing a spacecraft into a hazardous asteroid can truly change its path. And this was only phase 1. In 2024, Europe launched the Hera mission, designed to arrive at Didymos in 2026. Hera will carefully map the crater, study changes on Dimorphos's surface, and even look at how the strike altered its rotation and structure. Together, DART and Hera form a perfect model for future defenses. A strike mission to prove the concept, followed by a close-up analysis to refine our knowledge and improve future plans. The lessons from DART are already shaping how we think about Apophis and other risky asteroids. If another object were discovered heading our way, the same impact technique could be used to nudge it aside. But perhaps even more important than the science is the cooperation. DART may have been led by NASA, but European partners and observatories around the world played critical roles. It showed that planetary defense cannot be the project of a single country. Protecting the planet is a responsibility that belongs to all of humanity. Since then, the global defense framework has grown even stronger. In 2016, NASA created the Planetary Defense Coordination Office, which now manages everything from detection to deflection planning. It works closely with international partners to ensure that no discovery slips through the cracks. On a broader level, the United Nations established the International Asteroid Warning Network, where astronomers and agencies can instantly share data about new discoveries or potential impact risks. This network ensures rapid communication and a unified, trustworthy source of assessments. Alongside it, the Space Mission Planning Advisory Group works on the technical side, preparing guidelines and strategies for missions, if a real deflection is ever needed. These institutions exist because of the chaos during the early Apophis years, when different teams released conflicting predictions. That confusion highlighted the urgent need for clear authorities, standardized methods, and global coordination. Meanwhile, our tools for finding asteroids have advanced dramatically. In the early 2000s, surveys like linear dominated discoveries. Now, far more powerful systems, such as the Asteroid Terrestrial Impact Last Alert System and the Zikwi Transient Facility, are discovering thousands of new near-Earth objects every year, while also refining data on known ones. And the next leap is already on the horizon. NASA's NEO Surveyor, a space-based infrared telescope, scheduled to launch in 2027. Unlike ground-based observatories, it will specialize in spotting dark asteroids that are nearly invisible from Earth. This single mission could revolutionize discovery rates, particularly for mid-sized hazardous asteroids in the 100 to 500 meter range, objects large enough to cause regional devastation if they ever struck. In Chile, a game-changing observatory is taking shape. Set to begin operations in 2025, the Vera C. Rubin Observatory will launch the legacy survey of space and time. Its unprecedented combination of wide-angle observation, rapid scanning frequency, and remarkable sensitivity promises to transform the study of near-Earth asteroids. This isn't just about spotting rocks in the sky, it's about finding hundreds of thousands of previously unknown objects and mapping the orbits of known asteroids with extraordinary precision. For planetary defense, this represents a dramatic leap forward, giving scientists tools to monitor and react to cosmic threats in ways that were unimaginable just a decade ago. Yet planetary defense is far more than a technical exercise. Spotting an asteroid is only one piece of the puzzle. Humanity also needs the authority, resources, and international cooperation to act if a real threat emerges. The Apophis situation was a wake-up call in this regard. a seemingly small 2.7% chance of collision escalated quickly, sparking congressional inquiries, emergency funding debates, and diplomatic negotiations about global responsibilities. Even though further observations eliminated the immediate danger, the episode exposed a critical vulnerability. Without pre-established decision frameworks and rapid response protocols, even a short-lived scare can spiral into public panic and policy chaos. Modern planetary defense strategies assume early detection, often years or decades in advance, allowing time to design missions carefully and coordinate internationally. The DART mission validated this assumption, proving that kinetic impactors can reliably nudge asteroids off course when given sufficient lead time. However, the majority of near-Earth objects, especially the smaller ones measuring 10 to 100 meters, may not provide such generous warning. Some could appear with only months or a few years before a potential Earth encounter, demanding rapid response strategies that humanity has yet to fully develop. Scientists are actively exploring solutions, from pre-positioned deflection systems to ultra-fast mission architectures. While still largely theoretical, these initiatives embody the kind of forward-thinking approach born from lessons learned during the Apophis episode. The progression from the Apophis scare to DART's triumph illustrates the power of combined scientific insight and technological innovation. The frameworks established in those early years now stand ready to handle real, potentially catastrophic threats. This infrastructure functions as a form of cosmic insurance, investments in capabilities that ideally will never need to be used, but are indispensable in moments of crisis. Amidst these advancements, the methodical cataloguing of near-Earth asteroids has become the backbone of planetary defense. While sensational stories about interstellar visitors grab headlines, the true work involves cataloguing the thousands of more ordinary asteroids that quietly traverse our solar neighborhood. Understanding their orbits and behaviors allows scientists to identify which objects genuinely pose a risk. Near-Earth asteroids are divided into orbital families, each with different implications for planetary defense. The A10s orbit mostly within Earth's path around the Sun, yet their elongated trajectories occasionally bring them across our planet's orbit. These bodies are relatively predictable, but still require careful tracking. Apollo-class asteroids, on the other hand, cross Earth's orbit directly, making them especially hazardous. Apophis belongs to this category, along with many other asteroids that have caused genuine alarm over the past 2 decades. AMA's approach from beyond Earth's orbit, posing a potential future threat, as gravitational interactions can slowly pull them inward over centuries. Lastly, Atira's orbit entirely inside Earth's path, making them extremely challenging to observe because they are usually hidden in the sun's glare. Despite their elusiveness, every orbital group is studied rigorously to understand potential risk and prioritize resources effectively. Within these families, scientists focus on potentially hazardous asteroids, or PHAs. These are defined by a combination of size and proximity criteria, ensuring that only objects capable of causing significant regional or global damage are considered high priority. To qualify as a PHA, an asteroid must come within roughly 7.5 million kilometers of Earth and measure at least 140 meters in diameter. This threshold balances the likelihood of impact with the potential devastation. Smaller asteroids strike more frequently but produce only localized effects, whereas larger objects are rarer yet could threaten entire continents. Current catalogues list more than 2,000 confirmed PHAs, with hundreds more added annually as surveys improve and telescope capabilities expand. However, these numbers represent only the visible fraction. Statistically, tens of thousands of PHAs remain undiscovered, obscured by solar glare, or too dark for current optical telescopes to detect. The history of discovery reflects a rapid acceleration in awareness. In 1990, astronomers knew of fewer than 200 near-Earth asteroids. By the year 2000, that number had grown to over 1,000. Today, more than 34,000 NEAs have been catalogued, with roughly 3,000 new discoveries added every year. The largest objects, those capable of causing global catastrophe, are largely accounted for, providing reassurance that extinction-level events are extremely unlikely in the near future. Yet the smaller, regional threat asteroids remain a blind spot. Estimates indicate that fewer than 40% of PHAs in the 140-meter size range have been discovered. Detection limitations arise primarily from the sensitivity of ground-based telescopes. These instruments can only spot relatively bright asteroids against the backdrop of night sky glare, leaving dark or poorly positioned asteroids virtually invisible. These hidden threats are ordinary near-Earth objects, nothing exotic, yet they remain undetected simply because they are small, dark, or located in difficult-to-observe regions of the sky. The result is a knowledge gap, a blind spot in humanity's otherwise growing awareness of cosmic hazards. This is where new observatories, space-based infrared telescopes, and advanced survey systems are poised to make a difference. By seeing the universe in wavelengths invisible to the naked eye and scanning enormous swaths of sky in rapid succession, scientists can now locate objects that would have slipped past older systems. This expanded capability will not only increase the total number of detected asteroids, but will also refine orbit predictions for existing objects, giving planners more time to prepare mitigation strategies. In essence, the work being done today is slowly closing the gap between theoretical understanding and practical planetary defense, moving humanity closer to a state where every significant asteroid threat is recognized long before it reaches the vicinity of Earth. The implications extend even further when considering societal impact. Knowledge of potential asteroid threats influences public policy, emergency preparedness, and international coordination. The Apophis case highlighted how quickly uncertainty can escalate into political and social challenges. Governments must be ready not just with rockets and telescopes, but also with clear frameworks for decision-making, funding, and communication. Without these measures, even a relatively small risk could trigger widespread panic. The growing infrastructure, both technical and institutional, represents an investment in planetary security, one that combines science, engineering, and governance into a cohesive defense strategy. Ultimately, the story of near-Earth asteroids is not just about space rocks. It's about humanity learning to anticipate, prepare for, and respond to a universe that constantly moves around us. With better detection systems, international cooperation, and proven deflection techniques, the planet is better protected than ever before. But gaps remain, and the next decade will test whether the lessons learned from Apophis, DART, and Hera translate into readiness for the smaller, stealthier asteroids that could arrive with little warning. In this high-stakes cosmic chess game, every observation, every discovery, and every technological innovation counts. Humanity may never have to use these capabilities, yet the moment one asteroid turns from hypothetical to real, our survival could hinge on the very systems we are building today. Even relatively small asteroids can become sudden, high-stakes threats. Objects measuring just a few dozen meters might appear out of nowhere and unleash devastating effects if they strike populated areas. The Chelyabinsk meteor of February 15, 2013, is a stark example. At only about 20 meters across, far below the threshold for official potentially hazardous designation, it injured more than 1,500 people and caused millions of dollars in property damage. Its trajectory, coming from the direction of the sun, made pre-impact detection nearly impossible using ground-based telescopes. Imagine scaling that up. A 140-meter asteroid could wreak havoc across entire regions, threatening millions of lives. Yet countless objects of this type remain undetected, simply because they are too small, dark, or unfavorably positioned for conventional surveys. The solution lies in observing from space. Infrared detection offers a transformative advantage. Instead of relying on reflected sunlight, telescopes measure the thermal glow of asteroids, allowing even dark, low-reflectivity objects to be seen. The upcoming NEO Surveyor mission is designed specifically for this purpose. Optimized to find previously invisible asteroids, it will scan the sky in infrared wavelengths, where these objects naturally emit heat, bypassing the limitations that plague optical observations. With this approach, previously overlooked asteroids, the ones most likely to sneak past detection, can finally be identified and tracked. Scientists expect that this mission will dramatically increase discovery rates for asteroids in the size range that presents the greatest uncharted threat. Detection technology has advanced exponentially over the past 2 decades. In the late 1990s and early 2000s, near-Earth object surveys, relied on relatively modest 1-meter telescopes with simple CCD cameras. These instruments provided basic coverage but left vast portions of the sky under-monitored. Modern surveys employ far larger telescopes, ultra-sensitive detectors, and sophisticated software that automatically identifies and tracks moving objects. Systems like the Asteroid Terrestrial Impact Last Alert System, or ATLAS, operate multiple telescopes across Hawaii, South Africa, Chile, and Australia, providing near-continuous coverage of the sky. ATLAS can detect asteroids as small as 20 meters, only days before a potential impact, offering at least minimal early warning for Chelyabinsk-class events. Complementing these efforts, the Zwicky Transient Facility, ZTF, conducts rapid, wide-area surveys with a cutting-edge camera spanning over 500 megapixels. Each year, ZTF discovers thousands of new asteroids, while simultaneously refining orbital data on previously known objects to evaluate impact risks. The Vera C. Rubin Observatory, slated to begin operations in 2025, promises to dwarf all prior survey capabilities. Its legacy survey of space and time will repeatedly image the accessible sky twice a week, discovering potentially hundreds of thousands of new asteroids, while providing highly precise orbital data. Such accuracy dramatically reduces uncertainties in risk assessments, allowing planetary defense teams to prioritize the objects that matter most. But discovery is just the starting point. Each newly detected asteroid requires careful follow-up observations to determine its orbit with enough precision to evaluate impact potential reliably. This process can take months or even years, during which preliminary probabilities may fluctuate and generate public concern. The Apophis episode emphasized the importance of cautious interpretation during these early calculations. Initial estimates based on limited data can create misleading headlines. Most scares fade as successive observations refine orbital predictions, steering the object away from Earth. Successful mitigation requires both persistent observation and clear communication, ensuring that the public understands the difference between preliminary estimates and confirmed assessments. NASA's Center for Near-Earth Object Studies maintains the authoritative database for asteroid orbits and impact probabilities. Its automated Sentry system continuously scans all known near-Earth objects, calculating future impact probabilities and flagging any with non-negligible risk for immediate follow-up. This systematic approach represents a triumph of applied astronomy, an automated, always-on sentinel, safeguarding the planet by monitoring thousands of potential threats, years or decades before any could approach. The same methods that neutralize the Apophis threat are now embedded in a continuous proactive planetary defense infrastructure. April 13, 2029, will present a unique test for this infrastructure, an opportunity and challenge for science communication alike. Apophis, passing closer to Earth than any previously recorded asteroid of its size, will be visible to the naked eye under clear skies in Europe, Africa, and Western Asia. This spectacle presents an extraordinary chance to educate the public about asteroid science, yet it also risks generating undue anxiety. The paradox is clear: proximity does not equate to danger. Apophis will thread safely between Earth and the geostationary satellite belt, presenting zero impact risk for at least a century. Conveying this nuance demands precise messaging, balancing factual accuracy with public perception. Clear, consistent communication is essential. Scientists and agencies must emphasize safety up front, leaving technical details about orbital mechanics and scientific significance for later. NASA's approach has evolved considerably since the early years of uncertainty after Apophis's discovery. Safety assessments are now communicated first, followed by explanations of the encounter's value for research. The European Space Agency has adopted similar strategies, ensuring that public messaging remains unambiguous. Apophis will safely pass, and its scientific study is the focus. Lessons from the early Apophis scare underscore the importance of placing absolute safety assurances ahead of technical discussions, avoiding unnecessary panic while maintaining trust in scientific institutions. Visual tools will be critical for public engagement. Graphics, simulations, and animations allow audiences to grasp distances, orbital paths, and relative sizes, making abstract cosmic events tangible. By showing exactly how an asteroid passes safely above our planet, While explaining the scientific data behind these calculations, agencies can turn potential anxiety into curiosity and wonder. This approach fosters engagement, educates audiences, and maintains credibility, essential components for planetary defense outreach in the age of real-time media. The integration of advanced detection, robust follow-up procedures, and strategic communication forms a comprehensive planetary defense ecosystem. By identifying threats early, refining orbital data, and clearly conveying risk, humanity gains both time and knowledge to act when necessary. Systems like NEO-Surveyor, Atlas, ZTF, and the Veris-C Rubin Observatory operate in concert, combining ground-based and space-based capabilities to create a layered, resilient defense network. Meanwhile, the lessons learned from Apophis and other close encounters inform not only detection and response strategies, but also the critical human element of public perception. In the cosmic chessboard of asteroid defense, every observation, every calculation, and every message matters. Each plays a role in ensuring that when a real threat arrives, we are prepared to respond effectively. Visual representation is one of the most effective ways to convey both the proximity and safety of a close asteroid flyby. Accurate scale diagrams illustrating Earth, the Moon's orbit, geostationary satellites, and Apophis's trajectory allow audiences to immediately grasp the distances involved and understand why such a close approach does not translate to danger. These visuals must be carefully designed to avoid fear-mongering while emphasizing the genuine scientific significance of an asteroid passing within familiar cosmic landmarks. Timing is also key. April offers ideal weather for evening observations in the Northern Hemisphere and coincides with numerous astronomy outreach events. But the asteroid's visibility is mostly limited to the Eastern Hemisphere, requiring coordination across countries and organizations to maximize educational opportunities. Amateur astronomers around the globe are already mobilizing to participate in observation campaigns for Apophis. These citizen science efforts not only enhance public engagement, but also produce valuable data that professional researchers can integrate into ongoing studies. The International Astronomical Union has collaborated with these communities to create standardized observation protocols and data sharing procedures, ensuring that amateur contributions maintain scientific value. Social media presents another layer of complexity. Numbers like closer than geostationary satellites are irresistible for sensational headlines, but they can also spread misinformation and unnecessary panic. Planetary defense experts are preparing strategies to counter false narratives while maintaining credibility. Preemptive educational campaigns aim to equip the public with context, explaining why close proximity does not mean imminent danger. Many will instinctively assume that any near miss with satellites could cause collisions or unexpected trajectory changes. Translating complex orbital mechanics into accessible language becomes crucial. Audiences need to understand how precise calculations confirm safety without oversimplifying the science. Apophis provides a teaching moment in contrast to media sensations like interstellar visitors, which make headlines despite posing no threat. Unlike exotic objects that capture attention purely because of their origin, Apophis is a legitimate member of the potentially hazardous asteroid population, offering a real-world example of risk assessment in action. This distinction allows educators to explain why some cosmic events demand attention and resources, while others are mere curiosities. Schools and universities are already developing curriculum materials using the Apophis flyby to demonstrate orbital mechanics, gravitational perturbations, and statistical risk assessment. Students will gain hands-on understanding of how scientists monitor and predict asteroid behavior, anchored by a tangible, highly visible example. The asteroid's journey also illustrates how planetary defense operates and practice. Apophis evolved from an object with uncertain risk to one confirmed as safe, showcasing the scientific method at work. Hypotheses are tested, uncertainties reduced, and conclusions drawn from evidence. Despite early media alarm, the process reflects science functioning as intended. Public engagement activities can emphasize these successes, showing how sustained observation, precise measurement, and international collaboration transform potential threats into opportunities for learning and research. The infrastructure developed to track and study Apophis is not only a tool for one asteroid, it is a continuous safeguard against future hazards. Observatories on every continent have contributed data to refine its orbit, highlighting the international cooperation that planetary defense requires. Such collaboration transcends political boundaries and illustrates how shared challenges unite the global scientific community. Professional organizations coordinate messaging across countries and languages to ensure consistency. The International Astronomical Union's Commission on Astrometry maintains guidelines for risk communication, stressing clarity, accuracy, and context suitable for public understanding. These protocols standardize language describing Apophyse's safety, reinforcing trust in the information delivered. Authoritative sources become crucial during periods of heightened attention. NASA's Planetary Defense Coordination Office, the European Space Agency's Space Safety and Security Program, and the United Nations International Asteroid Warning Network are the go-to references for accurate information. Effective public communication directs audiences to these trusted sources while countering misleading reports from less reliable outlets. Scientists involved in Apophis studies undergo media training to communicate clearly. Interviews begin with unequivocal safety assurances before discussing technical or scientific details. This approach ensures that the public grasps the bottom line immediately, building confidence without dismissing the asteroid's scientific significance. Apophis also serves as a testament to decades of sustained investment in planetary defense. The observational capabilities, analytical tools, and collaborative networks that converted potential alarm into educational opportunity represent a long-term commitment to protecting humanity from cosmic hazards. Polling from previous encounters suggests that clear, consistent messaging from authoritative sources maintains public trust in science. Avoiding mixed messages, unnecessary jargon, or ambiguity prevents confusion and reinforces the credibility of official safety assessments. Beyond the immediate flyby, the event provides a platform to discuss broader cosmic risks and humanity's place in space. While this particular asteroid poses no threat, the existence of potentially hazardous asteroids in general underscores the need for ongoing observation, research, and preparedness. Educational initiatives linked to Apophis highlight not only astronomy, but also transferable skills in risk analysis, scientific reasoning, and evidence-based decision-making. These skills are valuable across diverse domains, from evaluating medical treatments to interpreting climate data to assessing emerging technologies. The ultimate measure of Apophis's educational impact will extend beyond understanding this single flyby. Success will be reflected in a public capable of discerning credible scientific information from sensationalized media, able to appreciate the methods and reasoning behind planetary defense efforts. As April 13, 2029, approaches, the global community faces its most significant test of science communication since the original Apophis scare a quarter-century earlier. With 2 decades of experience, standardized messaging protocols, and preemptive educational outreach, planetary defense organizations are better prepared than ever to demonstrate that proximity does not equate to danger. However, the story does not end with the April 13th flyby. In many ways, this close approach marks the start of the most scientifically productive phase of humanity's interaction with Apophis. Immediately after passing Earth, researchers will have the opportunity to gather unparalleled data on how a large asteroid responds to Earth's gravitational influence. Continuous ground-based monitoring over subsequent months will refine measurements of its orbit, spin, and surface properties with unprecedented accuracy. Each observation will contribute to our understanding of asteroid dynamics, informing both current planetary defense planning and the development of future mitigation strategies. The aftermath of Apophis's April 2029 flyby will offer a rare glimpse into how a close encounter with Earth alters an asteroid's physical and orbital characteristics. Every trajectory shift, every subtle change in spin, represents a natural experiment that astronomers have long awaited. While the asteroid will continue along its path around the Sun, careful measurements will detect minute variations in its semi-major axis, orbital eccentricity, and inclination. More dramatically, its rotation period and the orientation of its spin axis could shift in ways that reveal the hidden internal structure of this massive space rock. 2 months after the flyby, the OSIRIS-APEX spacecraft will reach Apophis to begin an 18-month in-depth study. This mission will not just capture surface imagery, It will analyze the asteroid's altered gravitational field, examine tidal stress effects, and perform thruster-induced disturbances to expose and investigate subsurface layers. Every piece of data returned will feed directly into the next generation of planetary defense strategies, bridging the gap between theory and real-world response. Scientists will finally see how an asteroid reacts when a planetary-scale gravitational influence reshapes its orbit and spin. Understanding these dynamics is not just academic. The insights gained will allow researchers to refine predictions about how similar asteroids might respond to active deflection efforts, such as kinetic impactors or other mitigation technologies. Current deflection plans rely heavily on computer simulations that assume certain mechanical properties and internal coherence. Apophyse's encounter will provide empirical evidence to test these assumptions. If the asteroid behaves more cohesively than expected, deflection missions may require greater energy to achieve targeted trajectory changes. Conversely, if it proves less structurally integrated, interventions could be more effective than simulations currently suggest. Either outcome will directly influence the planning and design of future missions aimed at safeguarding Earth from potential collisions. The level of international cooperation displayed during the 2029 observations sets a new benchmark for planetary defense operations. Agencies including NASA, ESA, and observatories around the world coordinated efforts in ways never before attempted for a single asteroid. These partnerships demonstrate a scalable model for responding to genuine threats requiring rapid deflection missions. The observational and computational capabilities, honed through Apophis research, from advanced radar imaging to ultra-sensitive photometric tracking, will now benefit thousands of other near-Earth asteroids that may warrant detailed study in the future. Policy and governance frameworks also stand to evolve from lessons learned during this encounter. While Apophis poses no danger, it serves as a real-world test for international coordination in space safety. Protocols for data sharing, observation prioritization, and communication will inform how the global community responds when an asteroid does present a credible risk. The experience reinforces that scientific and political coordination must operate in tandem to ensure rapid, informed decision-making. Educationally, Apophis's journey will continue to inspire long after the asteroid passes. Its transformation from potential threat to confirmed safety case embodies the scientific process, formulating hypotheses, reducing uncertainties, and deriving conclusions grounded in evidence. These lessons transcend asteroid science, providing society with a framework for understanding and responding to low-probability, high-consequence risks. Whether applied to health, climate, or technological hazards, the principles of careful observation, iterative modeling, and evidence-driven policy hold broad relevance. Future asteroid discoveries will directly benefit from the infrastructure and procedural lessons derived from Apophis. Observational networks, computational tools, and international coordination mechanisms, developed and tested over 20 years, now operate continuously, offering early warning and risk assessment for newly discovered potentially hazardous asteroids. The upcoming NEO-Surveyor mission, launching no earlier than late 2027, will dramatically expand this capability. Operating in thermal infrared, it will detect dark, previously invisible objects, potentially uncovering hundreds or thousands of new PHAs in the 140-500 meter size range. Each new discovery will undergo an initial phase of uncertainty, followed by iterative observations that refine orbit predictions, just as Apophis's path was clarified. Most will prove harmless, but statistical inevitability guarantees that a confirmed collision course will eventually be identified, at which point these tools and protocols will form the backbone of humanity's response. The Vera C. Rubin Observatory, set to begin operations in 2025, will complement NEO-Surveyor by delivering precise orbit determinations for thousands of near-Earth objects annually. Its legacy survey of space and time combines unprecedented sky coverage, sensitivity, and observational cadence to minimize orbital uncertainty. These capabilities address challenges faced during the early years of Apophis monitoring and enhance predictive accuracy for future objects. Meanwhile, technological innovations driven by Apophis research continue to advance planetary defense. Radar imaging at facilities like Goldstone and Green Bank now resolves asteroid surface features with meter-level precision, Optical tracking systems provide astrometric measurements capable of detecting minute orbital shifts induced by forces such as the Yarkovsky effect. These represent permanent enhancements to humanity's cosmic early warning system, ensuring that detection, tracking, and characterization capabilities remain state-of-the-art for decades to come. The data collected before, during, and after the 2029 encounter is also likely to challenge existing theoretical models. How rubble pile asteroids respond to tidal stresses remains poorly understood, and Apophis offers humanity's first direct observation of these processes. Any unexpected behavior could reshape scientific understanding of asteroid mechanics, refining models used in both defense planning and broader celestial studies. Commercial ventures stand to gain from these insights as well. Private companies exploring asteroid mining or resource extraction require detailed knowledge of composition, internal structure, and mechanical stability. The characterization techniques developed for Apophis may inform future commercial operations, reducing risk and improving mission planning. Policy implications extend further, as Apophis's successful transition from threat to opportunity demonstrates the value of long-term investment in planetary defense infrastructure. Funding justifications for scientific research and space exploration initiatives may increasingly reference Apophis as a case study illustrating measurable societal benefit. Furthermore, international space law and governance frameworks may evolve to address coordination gaps revealed during the encounter, ensuring that future high-stakes scenarios are managed effectively and collaboratively. Even after the flyby, Apophis will remain a popular observational target for amateur astronomers. Its accessibility through small telescopes provides a platform for citizen science, enabling enthusiasts to contribute data that complements professional research. These long-term observations may reveal gradual changes in the asteroid's properties, offering further opportunities to study the effects of Earth's gravitational influence over time. Finally, educational initiatives around Apophis will leave a lasting legacy. Curriculum materials are being developed worldwide, using the asteroid's journey to teach orbital mechanics, statistical analysis, risk assessment, and the scientific method. By anchoring abstract concepts in a tangible, widely visible example, students gain hands-on understanding of how science works and how complex decisions are made based on evidence. Apophis's story serves as a bridge between scientific discovery, public education, and global preparedness, offering a multi-dimensional case study that will influence teaching, research, and planetary defense for decades. The story of Apophis isn't just about a single asteroid, it's a lesson in perspective. While 3 Atlas drifts silently through the interstellar void, captivating amateur astronomers and news headlines with its glowing tail, it presents no real danger to humanity. Its beauty and rarity make it fascinating, yet irrelevant to our survival. In contrast, Apophis represents the hidden truth of cosmic risk. Ordinary, predictable, composed of unremarkable rock and metal, it follows a stable orbit traced for millions of years, yet its near miss in 2004 and the ensuing decades of observation taught us everything essential about defending our planet. The mundane neighbor could have devastated civilization, while the spectacular visitor offers nothing but intrigue. This contrast highlights a deep flaw in human risk perception. We are drawn to the unusual, the mysterious, the unprecedented, often overlooking hazards that develop quietly and predictably in the background. Apophis embodies the threats that matter most, near-Earth objects whose danger grows from simple orbital mechanics, patiently accumulating risk over centuries. Meanwhile, the public's attention focuses on rare, sensational events, misaligning perception with actual threat. The lessons extend beyond asteroids. Consider solar storms, which can disrupt power grids, satellite networks, and astronaut safety, or orbital debris, increasingly perilous for spacecraft in Earth orbit. These risks are real, cumulative, and persistent, yet they fail to capture headlines or spark urgent action. Even among asteroid threats, the disparity is clear. Kilometer-sized objects grab attention as potential extinction events, though their probability is vanishingly small. Meanwhile, the 100-500-meter city-killer asteroids, capable of leveling entire urban regions, pose far higher cumulative risk, but rarely inspire public concern. Apophis exemplifies the type of object. Planetary defense must prioritize tangible, potentially catastrophic, and within our technological means to monitor and mitigate. Its 2029 flyby, combined with decades of observation, represents humanity's first opportunity to fully apply theoretical models, test deflection strategies, and evaluate international coordination under realistic conditions. The asteroid has become a living classroom, demonstrating the scientific method in action, from initial discovery through uncertainty to empirical validation and risk communication. The encounter also marks a cultural shift in how we relate to space hazards. Humanity has moved from passive vulnerability to active stewardship, building the observational networks, computational tools, and governance frameworks necessary to anticipate and respond to threats. Investments in radar imaging, optical tracking, and space-based surveys have matured into an infrastructure that provides early warning for thousands of near-Earth objects. Apophis serves as the prototype for applying these tools effectively, showing that preparation, international collaboration, and sustained observation can turn a potential disaster into an opportunity for learning and public engagement. Educationally, Apophis will continue inspiring long after its closest approach. Students, educators, and citizen scientists now have a concrete example for teaching orbital mechanics, risk analysis, scientific methodology, and evidence-based decision-making. The asteroid's journey from perceived threat to confirmed safety illustrates the evolution of understanding, highlighting the importance of observation, measurement, and iterative refinement. Public engagement campaigns can leverage this narrative, reinforcing scientific literacy and trust in institutions that manage complex, low-probability, high-impact risks. Economically, the return on investment is clear. The relatively modest funding allocated to asteroid surveys and characterization over the past 2 decades has yielded extraordinary dividends in knowledge, preparedness, and technology. Every telescope, radar station, and software tool developed to track Apophis will continue to serve planetary defense for decades, amplifying the impact of these initial expenditures. The asteroid demonstrates that investing in foresight, scientific, technological, and organizational, provides protection against events that may never occur, but would be catastrophic if they did. Looking ahead, Apophis's legacy will influence both research priorities and the next generation of scientists. Young observers watching the asteroid safely traverse the night sky may be inspired to pursue careers in planetary defense, aerospace engineering, or space policy. These human capital gains represent another long-term benefit, ensuring that expertise is continuously replenished to face future cosmic hazards. Yet, the Apophis story carries a sobering reminder. Despite 2 decades of technological advancement, international collaboration, and rigorous observation, Earth remains vulnerable to the fundamental forces that have shaped the solar system for billions of years. The question is no longer whether another potentially threatening asteroid will appear, but when, and the answer to that question depends entirely on whether the lessons learned from Apophis, both scientific and institutional, can be applied effectively in the future. The real legacy of Apophis is not the detailed data collected or the public fascination it inspires. It lies in the frameworks and capabilities it enabled. Observational networks, global coordination protocols, deflection strategies, and risk communication systems now exist precisely because this asteroid challenged us. They form a permanent safeguard, humanity's insurance policy against cosmic catastrophe, tools we hope never to deploy but cannot afford to lack. As 3 Atlas fades from our telescopes into the depths of interstellar space, and Apophis continues its well-understood orbit, the distinction becomes clear. Spectacle does not equate to risk, and danger is often hidden in the familiar. The extraordinary, while alluring, rarely threatens survival. The ordinary, if unobserved, could have ended it. Planetary defense is therefore a discipline of attention, method, and patience. It teaches us to prioritize, to measure, to act based on evidence, rather than spectacle. By the end of the 21st century, Apophis will likely be remembered not for its brief passage near Earth, but for how it transformed humanity's approach to cosmic hazards. It symbolizes the point where planetary defense matured, from ad hoc reactions to proactive monitoring, modeling, and mitigation. The asteroid that once seemed poised to threaten civilization may ultimately be remembered as the one that taught us how to protect it. The lessons of Apophis extend beyond the asteroid belt, providing a model for risk assessment, scientific inquiry, and international cooperation that will guide humanity in navigating an unpredictable universe. The challenge posed by asteroids isn't always the rocks themselves, it's how we as a species perceive and respond to them. Public attention tends to gravitate toward the exotic, the mysterious, the spectacular. 3 Atlas, with its interstellar origins and glowing tail, captured imaginations worldwide, generating excitement, headlines, and fleeting curiosity, yet it poses no tangible risk. In contrast, Apophis, a perfectly ordinary near-Earth object, reminds us where true danger lies. Its predictability, familiarity, and modest composition make it easy to overlook, but its potential consequences are far greater. This disparity in attention has real-world implications. Funding, policy decisions, and political will often follow public interest. When curiosity eclipses risk, essential programs, planetary defense surveys, radar tracking, deflection research may receive less support than they deserve. The story of Apophis demonstrates the payoff of sustained investment. Decades of observation, international collaboration, and technological development transformed a potential disaster into a controlled scientific opportunity. The systems created to monitor and characterize Apophis now operate continuously, providing early warning for countless other near-Earth threats. This infrastructure exists because previous generations recognized the value of focusing on ordinary hazards rather than chasing fleeting spectacle. Missions like NEO-Surveyor and facilities like the Vera C. Rubin Observatory reflect this philosophy. Rather than studying a single unusual visitor, these projects systematically survey thousands of asteroids, prioritizing completeness and reliability over glamour. LSST alone is expected to detect more new near-Earth asteroids in its first year than all previous surveys combined. Meanwhile, missions like DART focus on practical validation of deflection technologies using predictable, ordinary targets. The goal is effectiveness, not media attention. International organizations, the International Asteroid Warning Network, the Space Mission Planning Advisory Group, coordinate observation protocols, data sharing, and response strategies. They may not make headlines, but they provide the backbone of planetary defense. And science communication plays a crucial role in aligning perception with reality. High-profile events like Apophis's 2029 flyby offer opportunities to educate the public about genuine risk versus sensationalism. Clear, consistent messaging, paired with engaging visuals and accessible explanations, can build lasting scientific literacy, helping society distinguish between plausible threats and mere curiosities. Economically, this approach makes sense. Continuous surveys and investment in deflection capabilities cost far less than the consequences of a successful asteroid impact. And these tools often serve multiple purposes. Radar systems for asteroid characterization also support spacecraft navigation and planetary geology. Software developed for impact risk assessment informs mission planning for exploration and robotics. Yet the greatest danger may not be a particular asteroid, but human complacency. Successes like Apophis risk lulling policymakers and the public into underestimating the next hazard. The lesson from 3 Atlas versus Apophis extends beyond astronomy. It applies to climate change, pandemics, technological disruptions, all ongoing challenges that lack the drama of the extraordinary but demand sustained attention, planning, and investment. Ultimately, the universe operates according to physical laws, indifferent to spectacle or sentiment. Asteroids follow orbital mechanics, not news cycles. Our survival depends on recognizing the difference between fascination and risk, and prioritizing resources accordingly. The real threat isn't the rare, beautiful visitor from across the stars, it's complacency. The assumption that ordinary threats can be ignored because they lack drama. 3 Atlas teaches us about human curiosity. Apophis teaches us about preparedness. The balance between wonder and wisdom need not be exclusive, but when survival is on the line, wisdom must lead. The most important insight from these encounters may not be about the asteroids themselves, but about us, our instinctive attraction to the exotic, our neglect of the ordinary, and the challenge of aligning perception with probability in a universe that remains indifferent to human existence.